Hey everyone, in this video we are going to talk about section 5.2a, which is about integration by substitution of variables. We're probably going to refer to it as U-substitution though moving forward. So we've already learned a bit about how to determine simple antiderivatives by thinking of backwards deriving. So this is going to be our first of many more complicated integration processes that we're going to learn in this unit. So specifically, U-substitution can be used to undo the chain rule. This concept will be really important as later on we're going to see that there's often hidden U-substitution problems in other types of integration questions. So be ready to put your thinking cap on and enjoy.
What we're going to talk about today is what if I didn't already have the antiderivative for me? What if all I was given was the indefinite integral? How could we go backwards and figure out what function our antiderivative is? So with the e to the 2x, I know that the antiderivative of e to the x is e to the x. But now that I have something else in that numerator, or not the numerator, in the exponent with it, that's going to make it a little bit more complicated. So the U-substitution method we're about to learn is going to be how we undo the chain rule. Today we're just going to look at a couple of basic examples, and then we'll build up from there. Okay, so we have this U-substitution process. We'll see what all of that looks like in just a second, but we're going to find U. We're going to be given U in section A first. We're going to find the derivative of U. We're going to divide both sides of the equation by the constant. We're going to substitute and simplify, and then we'll anti-differentiate. All right, so basic steps. Let's look at A. So A, we are finding the antiderivative of sine of 3x dx, and we're going to let U be 3x. So what's going to happen with this u equals 3x, I can already kind of tell that that's going to be my u. So the u is always going to be the kind of like the inside function. So remember, the chain rule is used when we have something like f of g of x. We have a composition of functions. So that u is really what that inside function g of x is. So we're going to take that out so we can replace it with u. So we're going to have the integral, let's make this a little thicker, of sine of u dx. Now, one thing that we notice right here is that my variable we are integrating over and the dx part don't match. So we need to replace that dx with some sort of du. So how we're going to do that is we are going to take the derivative of both of these. So we're going to differentiate u equals 3x and derive each side with respect for itself. So let me write that down so you have that. All right, okay, so taking the derivative of u, well, the derivative of something that's linear is just 1, right? But now I need to say that I took the derivative of u. So this is going to become just du. Okay, now let's take the derivative of 3x. Well, I know that derivative is 3, but now we need to say that we took the derivative of x. So I'm going to add a dx onto this. So now I have du is equal to 3 dx. So I'm going to solve for dx and then substitute that back in over at our indefinite integral. So solving for dx really just is dividing both sides by 3. So we have dx is equal to du over 3. So I'm going to substitute that in for dx over here. I don't want to say equals because we're kind of showing a chain of logic. So I'm going to make sure that I put an arrow here. So this is going to be the integral of sine of u, and then substituting du over 3 for dx. This is what it looks like. Okay, now I can always pull the 1/3 out to in front of our integral since it's a constant. So sine of u du. Okay, so now that I have everything where the variables match, we are good to find the antiderivative. So, what is our antiderivative of sine of u? Okay, we'll think backwards. That's going to be negative cosine of u, because I know that the derivative of negative cosine is going to be positive sine. So I'll have 1/3 times negative cosine of u. Now, I see that we took that derivative, but now I need to add on a plus c. So we have to add on our constant. All right, well, we're almost done, but remember, we didn't start off with u's at the beginning. We started off with x's, so we're going to resubstitute what u was back in for u here. So this will be negative 1/3 of cosine of 3x plus c. And we can always check our work by deriving again, right? So the derivative of cosine would be negative sine. Okay, well, those negatives would end up making it positive. Cool. And then the derivative of 3x, well, here, I should just write this down. So if I were to derive this, okay, let's see. So we'd still have that negative 1/3. Cosine's derivative is negative sine, but I'd still have that 3x inside. Oops. The derivative of c is just going to be 0. Oh, I forgot. Wow, getting ahead of myself. Derivative of our inside is going to be 3, and then the derivative of c is 0. Okay, and then cleaning this up, those negatives are going to be positive. My 3's end up dividing to be 1, and so we just have sine of 3x. And hey, that's what we started off with. So this U-substitution process really does undo the chain rule. Okay, let's look at another one. So for b, we have the integral of 1 minus cosine of t over 2 squared times sine of t over 2 dt. So we're going to be told here that our u is 1 minus cosine of t over 2. We'll get better at choosing what our u's are, but really what we're looking for is what thing seems to be inside a function. I see that this is kind of inside something that's being squared, so that's why we're letting that be u. Okay, so I'm going to substitute that into my indefinite integral. So that'll be the integral of u squared, but I still have this sine t over 2 dt. So we're going to have to do something to change all of our variables to be u. So that's where we're going to take the derivative of both sides of our u equals 1 minus cosine of t over 2. Okay, so let's see. Derivative of u is du. Derivative of 1 is 0. The derivative of negative cosine is going to be positive sine. And then we have another chain rule going on here. So that's sine of t over 2. But now I need to multiply by a half, right? Because that's the derivative of t over 2. And then don't forget, we took the derivative of things with respect to t, so I'm going to add on a dt. So cleaning this up, du is equal to sine of t over 2 times 1/2 dt. Okay, so now we're going to do some substitutions in for our indefinite integral. So I'm going to solve for dt. There's actually a couple different ways we can do this, but I'm going to solve for dt first, meaning that I'm going to divide everything that's not a dt. Okay, and then once I have that, I'm going to substitute that in for dt over here. So we have the indefinite integral of u squared times sine of t over 2, and then in for dt, I'm going to write du over sine of t over 2. Okay, and can we agree that this dividing by a half is really the same thing as multiplying by 2 in the numerator? Yeah, okay, I'm going to add that in. So times 2 du. Okay, well now I see I have something interesting that happens. So I have a sine of t over 2, and I'm dividing by a sine of t over 2. So those terms are going to end up canceling. So what I have left over now is the integral of u squared times 2 du. Hey, that looks a lot nicer to integrate, so let's pull out that constant. So 2 times the integral of u squared du. Boom, now we have something that's nice and neat, and we are going to integrate u squared du. Okay, well let's think, how would we do that? Well, I'm still gonna have my 2 out in front. Actually, I think here I can do an equals, because this really will equal it. So equals 2 times, okay, I'm gonna add 1 to my exponent, so u to the 3rd divided by my new exponent is 3. And then I'm going to add a c on the end. Now that I have this written out, we're going to go back and we are going to substitute this in for u. So that will be 2/3 times 1 minus cosine of t over 2 cubed plus c. So there we have it. There's our antiderivative. So for this process, we're really going to have to think broadly and kind of think ahead about what things could be derivatives of other functions. So that's going to give us an idea as to what our du might be. And specifically, that can kind of lead us to what u might be. So we're really looking, when choosing our u, to find functions that are inside of other functions. So that could be a term that's like raised to a power, under a square root, something of that sort. When we're looking at finding u or identifying our du can never be in the denominator, it can't ever be raised to a power, inside a trig function, anything like that. The du is talking about with respect to u, and it has to be at the end of the integral. Let's see what that means. So in example 1, let's look at a. We're finding the indefinite integral, basically just meaning that we're going to try to find the antiderivative. So we have the integral of 5 sine t over 3 plus cosine t squared dt. All right, well, let's look for some sort of function that might be inside another function. So specifically, I see here that I have this 3 plus cosine t that's being squared. So that gives me an idea that that's kind of like a function that's inside like a something squared, a quadratic function. So let's let this be our u. U is equal to 3 plus cosine t. Actually, I'm going to write this up here. Okay, so let's find our du. So let's derive both sides with respect to whatever that variable is. So du is going to be equal to, all right, well, the derivative of 3 is just 0. The derivative of cosine of t, well, derivative of cosine is negative sine of t. Derivative of t is just 1. Okay, so that was my derivative of this, but I also need to make sure that I add on a dt to signify that we derived it with the with respect to t. All right, so what do we have so far? Well, if I were to replace my integral with the u, with whatever function we have designated as our u, we would have the integral of 5 sine t over u squared dt. All right, so I have my u, but I see I still have t's in there. So what we need to do is we need to solve for dt. So I can substitute that back in, and hopefully other things that have t's in it will end up dividing out. So solving for dt, I'm going to divide both sides by negative sine of t. I can already see here that I'm in a good position because I'm going to be dividing by sine t, and that's going to end up undoing the sine t that we have in the numerator. So over here, I'm going to have the integral of 5 of sine t over u squared. And now replacing dt with what we have designated as dt over here, well, that's going to be du over negative sine of t. Aha, so I see that the sine of t's are going to end up canceling out. So what do I have left over? Well, I'm going to have a 5 and a negative 1. So I'm going to pull those out to be in front of the integral. So that's going to be negative 5 out in front. Then we have the integral of 1 over u squared du. I'm now in a really good position because I see my integrand is only made up of things that have u's in it. So we're good to start anti-deriving now. I'm just going to rewrite this. That's going to be like negative, actually, let's put an equal sign in between. So that's going to be negative 5 times the integral of u to the negative 2 power du. All right, so how do we anti-derive? Keep forgetting my equals. Okay, well, I know that I'm going to add 1 to the exponent, so negative 2 plus 1 is negative 1, and I need to divide by that new exponent. Then I need to make sure that I add a plus c, just to recognize that there could have been a constant there. All right, so let's clean this up a little bit. Those negatives are going to undo each other, and then so that's really going to be like 5 over u plus c. Okay, I have everything good to go, so now let's take what our u was originally, let's substitute it back in. So we'll have 5 over 3 plus cosine t plus c. Boom, There we go. There's our antiderivative. Well, let's take a look at our next one. So for b, we have the integral of sine of 2x plus 5 dx. I can see right away here what my u might be. I have this 2x plus 5 inside of my sine, so let's let that be u. U equals 2x plus 5. And so now let's derive both sides. So that's du equals, okay, well, 2x is just going to be 2, 5 is just going to be 0, and then we drove this with respect to x. I'm going to add a dx on. Okay, before I even set anything up, I already know that I'm going to need to substitute in for dx. So dividing both sides, I know that dx is equal to du over 2. So plugging in what I know that this is equal to u, I know that this is equal to dx. I'm going to have the integral of sine of u, and then dx is being replaced with du over 2. So I'm going to pull that 1/2 out in front of my integral, and I just have the integral of sine of u du. Everything matches. We're all in terms of u, so we're good to start anti-deriving. So let's see. So this will be equal to 1/2. And then let's think, what function gives us a derivative of sine? Well, I know that the derivative of cosine of t gives me a negative sine of t. So if I were to make that a negative cosine of t, its derivative would be negative sine of t, which would end up making it positive. So sine of u's antiderivative is going to be negative cosine of u. Then we've got to end on that plus c. Okay, so let's finish this off. Let's resubstitute u back in here. So we'll have negative 1/2 cosine of 2x plus 5 plus c. And if you're ever not convinced that you've actually done this correct, we can always take the derivative of it again, and we should always end up back where we started. So we should end up with the integrand of our original integral that we had. Try it out yourself, just in case you're not convinced. All right, okay, so looking at c, I see that we have the integral of the square root of natural log of x over x dx. Again, we're trying to find some sort of function that's in a function. So I see that we have this natural log of x that's inside a square root. So let's let that be our u. So let's let u equal the natural log of x. Okay, let's derive both sides. So du is equal to, well, natural log of x is integral, or derivative is 1 over x, and we drove that with respect to x. So solving for dx, I'm going to multiply both sides by x, so that's going to be x times du. Okay, so let's make these substitutions into our integral. Our u substitutions, in fact. That sounded weird, I don't know why I said that. Okay, so we have the integral of, we said that u is the natural log of x. We still had an x in the denominator, and then substituting in for dx, we have x du. I see that my x's undo each other, they divide to be 0, so it's going to be equal to the integral of the square root of u du. Or, rewriting that, that's the integral of u to the 1/2 du. I see we're all in a good place. I'm only in terms of u, so anti-deriving, I know I'm going to add 1 to the exponent, so that'll be u to the 3/2. And I need to divide by that new exponent. Then we're going to add c. So cleaning this up a little bit, that's going to be 2/3 u to the 3/2 plus c. And now I'm going to remake that u substitution. So here we go. So this is equal to 2/3 times the natural log of x to the 3/2 power plus c. I don't know why. Hopefully you can't see that my screen keeps getting like lighter and brighter, but that's driving me nuts. Cool. Okay. So in this case, we were looking at all of these examples where we had to find some sort of function in a function. Well, this can get a little bit more tricky once we get into some other trig functions. So turning our page over, we're going to do a couple more examples with u substitution and trig. So looking at a, I see that I have the integral of tangent squared x times secant squared x dx. So this is where it's going to come into play, where we have to kind of think of what could be our du. So which one of these terms could be the derivative of something else? Well, I know that I could really rewrite this integral. Like, imagine that we rewrote this integral as tangent x squared times secant x squared dx. So we're trying to think about which one of these functions could potentially be our u, and what would its corresponding du be? Okay, well, if I took the derivative of tangent of x, that would be secant squared x. And if I took the derivative of secant of x, that would be secant x tangent x. So do we see either of these functions showing up in our original integrand up here? And you might think, yeah, okay, like secant squared x showed up right here. So that could mean that tangent was our original u. I see that it's going to be kind of tricky to do if we chose secant, because that would already be like our secant squared, but I'd need like another secant in there, so I could have like secant tangent. It's just not going to end up working out. So that means that our u for a is going to be tangent of x, and our du, therefore, is going to be secant squared x, and then I'm going to add on to that dx. Okay, so let's make those necessary adjustments in here. So we'll have the integral of u squared times secant squared x. Ooh, okay, let's actually solve for dx here. So dividing both sides by secant squared x. So I know that dx is going to be equal to du over secant squared x. So making that substitution, I have du over that. Aha, and then I see my secant squared x's are going to undo each other. So again, we have the integral of u squared du. So now that everything is just u, we're going to anti-derive. So adding 1 to the exponent will be u to the third, dividing by that new exponent and adding c. And now, since I found that antiderivative, let's remake that u substitution in for here. Okay, so that's going to be equal to, actually I don't think equal to, we have to be kind of careful. You'll notice here that I go back and forth between using arrows and using equals. So when we say that something is equal, we're really saying like this statement that we've written is equal to something else. Arrows instead means that it implies. So I don't want to say that this is equal to something, like I just go back and forth. I'm just going to be careful. Let's just use an implies arrow in here. So I'm going to say that this implies that it's tangent cubed of x over 3 plus c. Or if we wanted to, I could write this as 1/3 tangent cubed x plus c. Okay, last example that we're going to do in this video, let's look at b. So we have the integral of sine of 2t plus 1 over cosine squared of 2t plus 1 dt. So right off the bat, you might notice that there seems to be like a lot of functions inside functions here. So I can already see right away that I have this like 2t plus 1. So if we try to choose that as our u, okay, if we drove both sides, well, that's just going to become 2t, or 2 dt. I see that we're going to have a hard time because, okay, well, where do I make that u? Do both of them get u's? Do I have like cosine sine u over cosine squared u du? It's just not going to end up working out because we end up with those sines and those cosines. We want to end up with one function that we can easily take the antiderivative of. So in this case, choosing 2t plus 1 as our u is just not going to be enough. So we need to think of something else. That's definitely going to be part of it, but we need more. So where over here do I see some sort of function and a function? Well, I kind of see that right here, right? Like I have cosine squared of 2t plus 1. So what if we thought about this as cosine of 2t plus 1 squared? So now what if we let our u be that cosine function? It still includes that 2t plus 1, but I think we're going to end up taking care of our sine problem up in the numerator. So deriving both sides, I have that du is equal to, well, derivative of cosine is going to be negative sine of 2t plus 1. But this is going to be a chain rule, so I also have to take the derivative of the inside. So that's also times 2 and then times dt. So solving for what dt is, so we can make that substitution, that'll be du over negative 2 sine of 2t plus 1. So let's make these substitutions into our integral, and let's see if things end up canceling out. If they don't, well, then we'll go back to the drawing board and we'll try to adjust our u again. So I'll have the integral of sine of 2t plus 1 over, well, we said that cosine of 2t plus 1 was our u, so that'll be u squared. And then we said that dt was equal to this. So times du over negative 2 sine of 2t plus 1. Cool. Okay, so now I see I have that nice property here where those signs are going to end up undoing each other. Nice. That's exactly what we're looking for. So I'm going to factor out this negative 1/2 out in front of the integrand. So I'm going to have negative 1/2 over 1 over u squared du. Aha, now my integrand is only made up of u's. So if I write this just a little bit differently, we'll be in a good place to antiderive. All right, here we go. So let's add 1 to our exponent. So that'll be u to the negative 1, and I'm going to divide by that new exponent and add c. Cleaning this up a little bit, I see that my negatives are going to undo each other. I can bring that u to the denominator. So that'll be 1 over, I'll do this right. Yeah, we're doing great. We're doing great, everyone. 1 over 2u plus c. So now we can go back. Let's substitute back in our u at the very end. So 1 over 2 times cosine of 2t plus 1 plus c. All right, there you have it, folks. There's our U-substitution. So again, it's just going to come down to, can we identify the functions in a functions? It just takes practice. It's okay if you don't have it right now, but we'll get better at it. I'll see y'all later.